All right, guys, it's Higgy again for all you physics wizards. All right, today we're going to be talking about kinetic energy and its formula and its uses. Okay, it's a pretty simple formula. EK equals 1/2 mv squared. All right, so all that's telling me is that I need a mass. I need something with some mass, some matter to it, like this calculator, and it needs to be moving at some sort of velocity, and I can find the kinetic energy. Kinetic energy is moving energy. We've been talking about potential energy, which is stored energy. This is the actual stored energy turned into kinetic energy. So if I take my little calculator and I throw it, then it has some energy. All right, and I've done some work to it, which equals the amount of energy that it has. All right, so simple enough. Let's have a little problem here. Car, 1,500 kilograms, traveling at 70 meters per second. All right, so you have this car, it's moving in whatever direction, doesn't really matter. All right, so I just plug my numbers in. All right, so let's do it right here. EK equals 1/2 the mass, which is 1,500 kilograms, times 70 meters per second. All right, and when I do my math, it's not that difficult to do. When I've done my math, I see that I have, I've already done the math here somewhere, 3,675,000 joules of energy. That's how much energy the car has. That's how much kinetic energy the car has while it's moving. And that kind of has to mean that it had to have that much potential energy before it started moving. That also means that it had to have that much work done to it for it to move that fast. Okay, just think about it in those kind of terms. Don't get overwhelmed with it. It's a pretty simple formula. That's a basic problem. Let's make a little more involved situation. Let's get involved in a little more in-depth deal. Let's look at our little ball situation that we've had. Maybe it's 50 kilograms and it's 100 meters on a 100-meter clip. All right, we want to know how much kinetic energy it has down here in the bottom. What is its EK down here, right at the bottom? All right, so we need to know then its mass, and we have that, but we need to know its velocity down here, but we don't have the velocity, we have a distance. All right, now if you remember back from, I don't know, sometime in 2017, we had the situation where if we knew the distance, we could figure out how long it took to fall, and we could also find out the velocity that it was falling at when it hit the ground, or at whatever level we wanted to measure it at. We could find the velocity at 100 meters, 50 meters. All we needed to know was the distance. Because we have this formula that says this. The second velocity, when you square it, it's equal to squaring the first velocity up here plus 2 times the acceleration and the distance. All right? And so this should look semi-familiar to you, so we're going to use that formula to help solve this problem. All right? Now, there's a couple things going on here to jog your memory. This thing's initial velocity, what is it? It's sitting at the top of the hill. That's right, it's 0. So this initial velocity here just falls out because it's 0. Now our formula is pretty simple. All I've got to do is get rid of that square thing right there, whatever it's exponent or whatever it is, and now I can find my v. And the way that I do that is I find the square root of the other side. All right, and now that I've done that, I have enough information to find the velocity that I need. Because at this point, I have the square root of 2 times acceleration due to gravity. Acceleration is something speeding up or slowing down. And here the ball is obviously speeding up because of gravity. And that number is, that's right, 9.8 meters per second squared. All right, so, and then I know the distance that it's fallen. It has fallen, which is 100 meters. So I just plug that in. And then when I run my numbers, it's not that too terribly difficult to find out the speed of this thing is 44.27 meters per second. All right, so that's my velocity that I'm going to plug in here to help find my kinetic energy down at the bottom, because that's how fast it was going at the bottom, right when it hit the bottom. All right, so then I just plug my numbers in. So EK equals 1/2, 50 is my mass. I'm just going to put the numbers here because I'm running out of room. 44.27 meters per second. And when I do that math, it's not that too terribly difficult to see that I have 48,995.82 joules of energy at the bottom. That's how many joules of energy I have at the bottom of this thing. And that's kind of makes sense because that car, remember, was a lot bigger and moving faster. It had over 3 million joules of energy. Well, this one has 48, right at 50,000. And it's a smaller ball, and it's not moving as fast as the car was. The car was moving at 70, so it was moving at 44. So I'm going to write this number here because I want us to keep it in the back of our mind what's going on. This is the amount of joules there are in the rock right as it hits the bottom. Because I want us to look at something else. I want us to look at a situation where maybe it has only fallen 75 meters. All right? And if I do that, it's very similar to comparing it to the car because if I do my math correctly, what I'm going to see is that this number, this right here, because it's not as moving as fast, it hasn't fallen as far. It hasn't had as long to speed up. I should find out that the energy here should be less than it is at the bottom. The kinetic energy the moving energy should be less. And so to do that, I have a mass, I know that, but I don't have a velocity at 75. So what I've got to do is use this formula again, and I'll write it all out so that you can kind of see it again. And then we know that this falls out because the initial velocity is 0. All right, and so this v then becomes the square root of 2ad. All right, so I'll plug my numbers in, my 2, the square root of 2 times 9.8, that's right. And my distance is how much? 75 meters, that's right, because that's how far it has fallen, all right? It's 25 meters from the ground, but it has fallen 75. You got to kind of put yourself in the problem. All right, so when I do that and I find that number, it's 38.34 meters per second. And that's the number that I'm going to plug in here to find out what my kinetic energy is at 75. So I just plug it all in again, and it's 1/2 the mass is always 50 in this case, and velocity is 38.34, and I square that. I don't think I put the square on that other one, but we've got to square it up here. And so when you do that, that number becomes 36,748.89 joules. And so I see that that is smaller than that because I don't have as much kinetic energy right there. All right, but I did this problem because I want you to keep that in mind. The kinetic energy increases the farther that it falls. The faster that it goes, the farther that it falls. Okay, that's a pretty big piece of the puzzle. As we go into tomorrow, when you get this video, you're going to have a sheet with some kinetic problems on it. And then that'll be, tomorrow's Wednesday, that'll be Wednesday. And then Thursday, I've got a combined sheet. And then Friday, we're going to have a quiz. All right? So go get your work done and watch the video as much as you need to. Ask me some questions, and I'll see you when I see you. You're awesome.